I will follow. Right. Well, very welcome to Alex Stottmeister. I will just briefly introduce you here. You got a PhD, I believe, in 2015 from Erlangen, after which you did postdocs in Rome, Münster, and now Hanover. You're working at the interface between quantum spin models, quantum information, and renormalization. Thanks for coming, Alex.
Yeah, well, many thanks for the invitation and the opportunity to present this work, which basically goes back to the last few years. So yeah, the title of the talk will be on the scaling limit of the Ising anyon chain. And I should point out that this is current work in progress with Daniela Cadamuro, also from Leipzig, and some of the people present in the audience, and with Tobias Osborne from Hanover. And it's based on previous work with Vincenzo Morinelli and Gerardo Morsella and Tanimoto, who are all in Rome at the moment. And I have to give you a brief outline of the talk. So first, I would want to just briefly motivate what this talk, or what the main goals for this talk are, and what is the context. And then I will discuss the main technical tool I want to use to discuss this scaling limit, which I call operator algebraic renormalization. And then in a third part, I want to apply this to the so-called transverse field Ising model, which obviously refers to this Ising anyon chain, which is a kind of 1+1 dimensional incarnation of the classical 2-dimensional Ising model. And in the context of this model, I want to explain to you how conformal symmetries can be recovered via this operator algebraic renormalization procedure when you discuss the scaling limit of this spin chain model at the critical point, and also how operators like specific, say, primary fields of the resulting CFT, like the disorder parameter, or additionally the order parameter, can be recovered by this method. And as a final point to discuss, I want to tell you something about how this method can be applied in the context of quantum information theory, and especially in the context of quantum simulation of quantum field theories. Yeah, and well, let me start with the first point. So what I want to talk about is the overarching goal for this project is essentially the construction or approximation of real-time QFTs and CFTs via lattice models. And of course, this touches essentially upon 3 points. So the construction approximation here, what I want to understand by that is basically the mathematical implementation of constructing QFT or CFT models from lattice models via the method of the renormalization group in the sense of Wilson and Kadanoff. And well, the lattice models, essentially, I want to use those models because they are things which are easily related to models which are important in quantum information theory, for example, spin models, in which you can naturally simulate on quantum computers. So in a sense, if you're able to give a rigorous construction of certain QFT models with, say, error bounds referring to how good your lattice approximations are, then you basically obtain via this construction, or that's at least what I want to argue, sensible simulation algorithms for these QFT models on future quantum computers. And of course, the construction of QFTs and CFTs in this context refers to understanding the RG fixed points of the implementation, the Wilson-Kadanoff renormalization group I want to discuss. And there are always these kind of dual pictures where either you think of the physical content you are describing as the short distance physics of a proposed continuum model, or you think about the long distance physics. If you think about condensed matter systems and continuous phase transitions in this context. And another important motivation for this project is that, in a certain sense, as I was pointing out, I want to do this in real time. So the method, in a certain sense, should complement existing Euclidean or imaginary time frameworks for the construction of QFT and CFT models via RG methods. And well, of course, there are a lot. This subject has a long history, and I don't know, many of you were probably present at the previous talk by Alessandro Giuliani, which I would like to refer to for like further references for this RG methods in the Euclidean context. And mathematically, you could say that the main tools I want to use here are of an operator algebraic nature instead of using classical probabilistic methods, which are, if you want, at the heart of the Euclidean or imaginary time framework. And in a sense, these operator algebraic methods are somewhat close to the original construction of the P-phi-2 models, like Lim and Jeffy, but the implementation of the renormalization group is, in a sense, in a similar spirit as the method proposed by Balaban for the RG implementation in the Euclidean context. And to also comment on the relation to quantum information, I think it's somewhat evident that the RG somehow gives you a natural connection between quantum information and QFT, especially because in quantum information, you're usually dealing with, in a sense, finite dimensional systems or condensed matter systems, and they could be seen as a kind of effective approximations of QFT models, and so the renormalization group gives you a kind of mathematical implementation of how to connect these effective models to QFT models one would be eventually interested in. And this brings me already to the second section of the talk. So I just want to briefly recall what I mean by operator algebraic renormalization. And as I was pointing out before, this is essentially an implementation of the Wilson-Kadanoff renormalization group in the following sense. So to define the renormalization group, what we are actually doing is we consider a given sequence of quantum systems are defined at certain effective scales, which I'm here basically encoding into this tripel of data. So I have at each, say, logarithmic length scale n, I have an effective set of observables or basic fields of the theory which act on a certain Hilbert space relevant to these effective degrees of freedom, and the dynamics of the model I encoded into a Hamiltonian, an effective Hamiltonian at this scale. So we are essentially talking about effective Hamiltonian quantum systems indexed by length scales. And the picture you should have in mind in that case, especially in the lattice context, is that you're thinking about coarse and finer and finer lattices, where, for example, you have at each vertex of your lattice given on-site algebra of observables and on-site Hilbert space, and the Hilbert space of the total system, and also the algebra of observables of the total system at that scale is just given by the tensor product over these lattice sites. But of course, and I mean, this is the natural setting in spin models, but of course, you could also attach the data to the edges or faces of the lattice model. That's not, so this detail is not too important here. And what the renormalization group then is in this context is essentially an object that provides you with a link between these different effective systems. So first you have just the sequence of effective lattice models, which are kind of detached from one another, and defining the renormalization group basically means that you define a set of maps that relates the systems at different scales. And in the context of, or in the original context of Wilson-Kadanoff, this is usually done at the level of density matrices or of states of your effective systems. So what you're typically doing there is that you consider the canonical density matrices of your given effective systems, and you define so-called coarse graining maps, for example, like the box bin transformation that maps you from the density matrices or the states of your system at a fine scale to those at a coarse scale. And the typical requirements for this transformation are that you want complete positivity of the map, you want the maps to be trace preserved. So essentially these objects should be quantum channels, and you want a kind of semi-group property so that if you iterate the coarse graining, that this is the same as just going the whole way in one step. Of course, these conditions can be weakened to some extent, but that's like the context I want to work with here. Maybe just to illustrate why you would choose these properties. Well, the trace preserving property is of course chosen because you basically want that your renormalization group preserves the probabilistic interpretation of your theory. And in the physics literature, this is usually expressed by the fact that you have a certain invariance condition of the partition, or for the partition function, meaning that if you look at in the context of these canonical density matrices, if you look at the partition function of your given effective Hamiltonian at a fine scale, then your renormalization condition should basically preserve this partition function when you coarse grain the Hamiltonian to a coarser scale, and then evaluate the partition function there. Then the values for these partition functions should agree, and this is essentially requiring that you preserve probability, or in a certain sense you increase, or by the coarse graining procedure, you increase the density of states when moving from a fine scale to a coarser scale. Okay, and in the operator algebraic formulation I want to use, we basically dualize this picture in the sense that we go from these coarse graining maps on density matrices or on states to the operationally dual quantum channels on the observable algebras. And this has some basically some nice consequences for how to set up the scaling limit in the end, or what the actual scaling limit should be. So what we are doing now is we define we consider the operationally dual channels, which map your observables from a coarse scale to the observables at a fine scale, meaning that these maps essentially encode how observables at the fine scale are resolved, or at the coarse scale are resolved into observables at a finer scale. But in essence, this operation still encodes the same thing as the coarse graining operation before, but it's operational dual. And then these properties, which we have for the coarse graining map here, just translate into the analog properties for these dual quantum channels, in the sense that we again want complete positivity. The trace preserving nature now just becomes the unitality of these maps, and the semi-group property is essentially the same as before, but of course we invert the arrows, so the direction of these contractions here are inverted. And now the original renormalization group transformation is considered by just is formulated by just considering the pullback action of these refining maps on observables on the state spaces of the algebras of fields or observables at the effective scales. So the meaning that if you take an abstract state, so an expectation functional on your observable algebra, then you just at a given scale, then you consider its pullback to a coarser scale by these alpha maps, and that's the renormalization group transformation, which was before denoted by this calligraphic E here. So in a sense, this is kind of the central equation you want to look at, and you want to understand whether limit points of this operation of this renormalization group transformation exists when you fix a certain core scale, and basically generate a sequence of states, renormalize states by pulling down states from finer and finer lattice models to a given core scale at which you want to evaluate your renormalization group transformation. And to put this in a kind of more pictorial form, I think this is kind of beautifully summarized by the so-called Wilson triangle of renormalization. So if you look into one of the original papers by Wilson, basically formulated the problem exactly in this way of how to define a scaling limit, but using basically the Hamiltonian picture instead of this operator algebraic formulation. So what you do there is you start with your effective Hamiltonians, which are given over all the scales at which you consider your model, which is this diagonal sequence here. And at each fixed scale, you generate a sequence of renormalized Hamiltonians by basically using your coarse graining operation to move the effective Hamiltonian at finer scales to the scale at which you want to consider your scaling limit. And the question of the existence of a scaling limit in this Wilson language would then basically amount to asking whether you can construct a limit Hamiltonian, and whether this limit Hamiltonian is then stable under this renormalization group transformation. But in a sense, this, I mean, like conceptually, this picture is quite nice, but there's a kind of issue of how to make this mathematically precise. And in this context of operator algebraic renormalization, this is in a sense more easily realized. And instead of looking at the effective Hamiltonians, we look at a sequence of states which are defined by the dynamical input which we have at each effective scale. So typically you would choose these initial states here at all the fine scales. It's, for example, something like the ground state of your effective lattice Hamiltonian. So it already contains some kind of the dynamical information of your problem. And to achieve a sensible scaling limit, you would basically want to look at a model where you look at the ground state close to a critical point of the model. And what you do now is by using this equation here, so basically the definition of the renormalization group transformation on these states, you generate sequences of states on the observables at a given fixed scale by just pulling down the states to that scale from the final scale. So your initial sequence induces these horizontal sequences, and the question of whether you can get a scaling limit essentially is the question of whether you can find a convergent sequence for each effective lattice scale in this horizontal sense here. And then due to the fact of how this equation is set up here, a nice observation is that if you can ensure the convergence in these horizontal lines, you automatically obtain something that is stable under the coarse graining operation in the end. And it can be defined as a sensible state on a certain limit object, which will be just the inductive limit of your observable algebras, which is defined using these fine graining maps. So you basically use these fine graining maps for the observable algebras to define an inductive limit of these algebraic objects, and then the scaling limit, provided it exists, will define state on this inductive limit, and this pair of this limit state and this inductive limit algebra, that's what in the end defines your scaling limit and or your QFT model. And to get back a Hilbert space formula or Hilbert space type formulation of your theory from this algebraic data, you basically use the so-called Gelfand-Naimark-Siegel construction, which provides you with a Hilbert space, a representation, and a, say, vacuum vector for your QFT model just from the data that you have this scaling limit state and your inductive limit of algebras. And in a sense, this then defines your, if you want, your kinematical data for your quantum field theory. And on top of that, you would then also try to analyze questions of whether the effective dynamics converges to the continuum dynamics. And this is typically then set up in the following way. So it's kind of inspired by how you do this in the thermodynamic limit for example, quantum spin systems. Yeah? So you define the limit of dynamics in the sense that you look at the effective dynamics at a given scale. You restrict that to a coarser scale. This coarser scale will be fixed. And then you push these dynamics to the inductive limit algebra. And the question is now whether this object restricted to the yes, sorry, here's one typo. So it should be actually the other way around. It should be MN. So if you now consider the convergence of these effective dynamics restricted to a certain coarse lattice, and when that converges, so then you would say that the effective dynamics converges for observables relevant to this fixed coarse scale, and that's actually so this whole procedure is something which with my co-authors from Rome I checked for initially just for free lattice scalar fields, and it directly recovers the continuum scalar field models via this procedure. So basically, if you start from a lattice discretization of a scalar field, and you use the ground states of these lattice models as an input for this procedure, so as these effective states, this diagonal sequence here, then, and by correctly setting up these alpha maps here, you can generate this this vertical sequence of coarse graining stable states, and also this inductive limit algebra here. And this pair really defines via this GNS construction the continuum scalar field model you're looking for, and also the dynamics converges in this sense I was describing here. And now the work, what I'm currently working on, and where we already have obtained some results, is to carry this procedure out for a model which is not just a free field situation, but corresponds in a certain sense to a very simple interacting field, namely this transverse field Ising model, which is still kind of easier to treat than a general interacting model, but because of its integrable structure, but already also exposes additional difficulties. And of course, in the context of this Ising model, there's also the very interesting question whether you can show directly from the lattice via this idea of formulating the scaling limit that the scaling limit at the critical point is actually a conformal field theory. So that in a sense you can recover the conformal symmetry from the scaling limit procedure for the lattice model. Of course, this in the two-dimensional classical setting, this has, for example, been carried out by these methods using Schramm-Loeffner evolution. But I think it's interesting, especially from this perspective of quantum information theory and the possibility to simulate these models on future quantum computers, whether you can also do this directly in a real-time Hamiltonian setting. And to somehow already tell you something about the main result. So the main result will be that if we use this procedure in the context of this transverse field Ising model, then it's actually possible to directly show the convergence of certain approximations of the conformal generators via these methods, and the approximation of conformal symmetries will essentially follow the same idea as this convergence of dynamics in this, as I described before. So let me now just tell you something about the setup for the transverse Ising model. So in this case, we will work in finite volume, basically on a spin chain with periodic or anti-periodic boundary conditions. So our lattices are essentially just partitions of the circle of a certain length scale L, and we work in fixed volume. So each lattice, even though we increase the number of lattice points, describes the same spatial volume, which is this means that if we have a discretization length epsilon n and the number of lattice points to L, then basically the volume is fixed by this condition here. And the Hilbert space of each effective lattice model is just given basically by a tensor product of C2 Hilbert spaces, so a natural setup for a spin system. The observable algebra is the usual tensor product over all the complex 2x2 matrices at all the lattice points. So it's just the Pauli algebra, and with its kind of convenient basis given in terms of the Pauli matrices. And the Hamiltonian for this transverse Ising model is given in this form. So it's called transverse field Ising model because you have the usual spin-spin interaction in the three direction, and you have a transverse field applied in the one direction with and since we put it on the circle, the model, you also have to add a certain boundary term. And to keep the discussion simple, it's actually useful to use so-called mixed sector boundary conditions, because that somehow simplifies the calculation in the end, meaning that you have a boundary term that essentially involves the spin flip operator, which is just given by the product over all the sigma 1 matrices at all the lattice sides. And then in this model, so the link to the two-dimensional classical Ising model is actually that this model is just a continuous time limit. The classical Ising model, in the sense that when you put it into this transform matrix formalism, you take the continuous time limit into one direction for your transfer matrix operator, and then the logarithm of this limit basically produces this effective Hamiltonian. So that's kind of the connection to the two-dimensional Ising model, and it's known, at least I think, from the work of Schulz and Mattis in 1961, that you can exactly solve this model. And of course, the solution is very similar to the Onsager solution for the 2D classical model. And now the question is, how do we set up the scaling limit procedure for this model? And I already told you that basically I defined the input data for all the effective models at each scale. But to carry out the scaling limit procedure, we still need a sensible definition of the renormalization group transformation. And as I was explaining before, so the renormalization group transformation should be a map that takes your observables at a coarse scale to observables at a finer scale. So physically, what you want to do is you want to decompose your coarse observables into fine observables in a kind of sensible way. And to this end, it's actually advantageous, at least in this transverse Ising field model, that instead of working with the spin operators, you work with the representation of this model in terms of fermions, because for the fermions, it's relatively easy to set up a nice renormalization group transformation. So what we do at this point is we consider the so-called Jordan-Wigner transformation, which is a star isomorphism between the Pauli algebra of spins at a given length scale to a certain type of fermion algebra. And just for completeness, to remind you how this actually looks like. So you have a map that maps your spin operators into combinations of complex fermion operators, and the spin one, the sigma 1 matrix actually becomes this quadratic operator in terms of complex fermion operators, and the sigma 3 operator becomes a product of this linear combination of the equation annihilation operator at a given site and this string operator here, which is the so-called disorder parameter. And already at this point, you can basically see that although this map is an isomorphism between these two algebras, at a given effective length scale, this considering this map in the scaling limit becomes problematic because of this the appearance of this disorder parameter here, which contains a kind of string-like operator, which becomes kind of more formally becomes an infinite product in the scaling limit. So in a sense, you would expect that this isomorphism breaks down in the scaling limit, but nevertheless, we will work instead of with these Pauli algebras, we will work with this fermion algebras and try to reconstruct the, for example, this disorder parameter as a composite operator from the fermions in the scaling limit. So in this sense, there's some additional work to do. So you cannot just infer the scaling limit of the Ising model from the scaling limit of this fermionic model just from this algebraic data, but you still have to somehow show how to implement these the analog of this isomorphism in the scaling limit. And just to show you why this model is actually exactly solvable, well, if you reformulate the Hamiltonian of this model now in terms of the complex fermion operators, you find that it's actually a quadratic model. And since in this case it's even translation invariant, it's relatively easy to solve for the ground state of this model. And the ground state of this Hamiltonian in this fermionic formulation, that's the one which we will actually use as an input for the scaling limit construction, to obtain, on the one hand, in terms of the fermions, our inductive limit algebra, and in terms of these ground states, the scaling limit state. So now, how do we now set up these renormalization group transformations? Well, to motivate this, it's actually useful to go to the so-called one particle picture for this fermion algebra. So you can think of this fermion algebra at each effective length scale as basically the antisymmetric second quantization of a certain one particle theory. And the renormalization group transformations, they will be defined in terms of operations, or basically isometries at the level of these one particle spaces, which are then promoted by second quantization to maps between the fermion algebras. And in this whole context, it's actually also quite useful to introduce the dual momentum lattice, related to the spatial lattice, and because in this dual momentum lattice, it's relatively easy to distinguish the different relevant sectors for our scaling limit construction, namely whether we are working in the so-called Ramond or the Neveu-Schwarz sector, which means that we either use anti-periodic or periodic fermion operators. And it's actually the Neveu-Schwarz sector, so the anti-periodic fermions, which will give you the vacuum representation of the scaling limit in the end. Okay, and as I said, so the input for the scaling limit construction, that will be the ground state of our effective Hamiltonian, which is quadratic in our lattice fermion operators. So because of this, it's actually characterized just by its 2-point function. So in this sense, it's a kind of Gaussian state or quasi-free state, be more precise. And this quasi-free state is encoded into a certain projection operator on the one particle spaces. So if you evaluate this ground state on a quadratic expression of fermion operators, then you can basically determine its value by just evaluating this one particle projection operator with respect to the corresponding smearing functions of your lattice fermion operators. And this, just for completeness, so this thing can be explicitly computed, and it's just given in terms of the Hamiltonian, which is the one particle Hamiltonian in its momentum space representation. Okay, and yeah, one thing that is also relevant for the recovery of the conformal symmetries in the end is that this Hamiltonian is actually self-dual for a certain one particle space conjugation. So that's why you can actually decompose this model into two chiral halves in the scaling limit. And this conjugation is explicitly given on the one particle space by just the conjugation of the one particle vector and then rotating with a sigma 1 matrix in the representation I gave you. Okay, and another thing is that in the scaling limit at the critical point, it's actually useful to consider the chiral decomposition of your one particle space, which means that you use this so-called chiral projector here, which is compatible with this one particle conjugation. So in the sense, the Hamiltonian in the end is also compatible with this chiral decomposition, and each of these chiral halves of the theory that should give you a representation of the Virasoro algebra in the end. And yeah, so and the critical point in this model is actually, if you look at this quadratic model here, you can recast it into a form of basically free fermion lattice theory with a mass term, and the condition that you're at criticality then boils down to this this lattice mass vanishing in the scaling limit. That's the condition I was writing down here. So this lattice mass lambda n is basically is a certain combination of the coupling constant for the transverse field term and the spin-spin interaction. And if you let this lattice mass tend to 0 fast enough, you will approach the critical theory in the renormalization group limit. Okay, and now how do we set up the renormalization group transformations in this setting? Well, what we are doing here, as I said, is basically we want to understand how to decompose observables at coarse scales into those at finer scales. And in terms of this one particle picture, that means that we want to decompose one particle vectors at a coarse scale into one particle vectors at a finer scale. And in a sense, this naturally relates to the theory of wavelets in the following sense, that you can define so-called families of wavelets by scaling functions, and scaling functions are basically functions in L2 of the real line, which have a kind of self-similarity property in the sense that you can decompose the function at a given scale into a linear combination of its rescaled and shifted self. So that's this equation here. And these coefficients is what usually called a low-pass filter. And this is a kind of similar problem to what we are facing here in defining this renormalization group transformation at the one particle level. Because we want to decompose vectors in a certain coarse scale lattice into vectors in a fine scale lattice. So in this sense, the problem is the same. So we can use these low pass filters here to define such a transformation. So if we are given a scaling function which is defined in terms of such a low pass filter, we can use this low pass filter to define a transformation between vectors corresponding to a one particle space at a coarse scale into those of one particle vectors at a finer scale. And this and here basically added just a picture to illustrate what this equation in a sense really means. So the simplest example of a scaling function is just the indicator function of, for example, the interval 0 to 1, which of course, if you rescale this function by a factor of 2 and shift it, then you can decompose the original function at, let's say, unit scale into sum of itself and its shift itself rescaled at the scale 1/2. And interestingly, there are actually more complicated functions which also have a higher degree of regularity that do the same, but for a more complicated decomposition. And so this is what is shown in this second picture here. So here you have like a plot of the so-called D4 Debussy wavelet, which is a function that can be decomposed into linear combination of 4 times its rescaled self from the unit scale to the scale 1/2 with certain coefficients. And as I said, we will basically use these coefficients, these low pass filter coefficients, to define now isometries between one particle vectors at a coarse scale to one particle vectors at a finer scale. And this is just in terms of the, let's say, lattice point-wise this lattice representation of these one particle vectors. That just means that you spread out the coefficients of a one particle vector on a coarse lattice in terms of this low pass filter. And then the nice thing is that you can, if you do this, you can actually, by using the theory of these scaling functions, you can even define the asymptotic maps, or the embedding of a one particle vector at a coarse scale into the continuum limit, if you want, by just iterating this procedure. And iterating these maps, and what you will find is that this actually just corresponds to kind of discrete convolution of your coarse scale one particle vectors with the actual scaling function that is determined in terms of these low pass filter coefficients. And then by second quantization, we can provide, we can basically define our renormalization group transformations, our fine graining operations on fermionic operators in terms of these one particle operators, by just promoting them via second quantization. And these are the maps we will actually work with to connect the models at different scales. And a nice observation here is that because of the if you choose the extension of your low pass filter to be finite, so you only have finitely many coefficients, then these maps will be actually compatible with locality or anti-locality in this case for the fermion algebra, meaning that if you have a fermion operator localized in a certain region and you use this map, then because of the finite spread of this low pass filter, this thing stays localized in the scaling limit, and actually allows you to define local or anti-local algebras for the fermion operators directly in the continuum, directly via local objects on the lattice. So in this sense, you can even localize your construction, which is quite useful if you want to go also to the thermodynamic limit in the end. Okay, so yeah, having said this, so what we can now carry out this operator algebraic renormalization procedure, and what we will find is that this inductive limit algebra of our basic fermion operators is just CAR algebra of the L2 space of the circle we were approximating. And just because our low-pass filter gives us a wavelet basis over all these successive scales for the L2 space on the circle in the end. So this is actually, this A here actually just follows from B by how we have set up the problem. Now the next important observation is that we can even carry out this renormalization group limit if we start from the ground states. So what I mean by C is that if we go back to this figure here, we can, using these alphas I defined, we can carry out these horizontal limits here and obtain an explicit representation for this scaling limit of our state we are looking for at each scale, and we find that it's stable under these coarse graining maps. So in this sense, it defines a state on this inductive limit algebra which we have set up. So on A infinity, and provided we use this renormalization condition that the lattice mass scales appropriately depending on the lattice distance. And actually this condition that fixes whether we end up with a massive theory in the end or with a massless theory. And well, due to the integrability of the model, we can actually directly compute the scaling limit, and we find that the scaling limit is the expected, or the scaling limit of our state is really the expected limit, which we want to have for the massive continuum or massless continuum fermion model in the end. So it's again given as a quasi-free state, and in terms of a one-particle projection, and this just for completeness, I wrote down how this projection operator looks like, and that's the one which you would expect to obtain if you were just formulating the model in the continuum directly. So in this sense, via this procedure, we really recover this continuum state from the ground states of our lattice model. Okay, and well, this it's interesting here, so that's why I was pointing out to use these chiral projectors in the massless limits. So if you tune your scaling limit to be a massless fermionic theory in the end, then you will find that this one particle projection is essentially the chiral projector in the end. So that's why you can in the end restrict this state in a sensible way to the two chiral components of your model. Okay, and this now brings me to the specific situation we have in the massless case, and how we can actually recover conformal symmetry, and how one should look at the disorder parameter as a means to reconstruct the order parameter in the scaling limit procedure in the continuum. And well, to first focus on the conformal symmetry, here there has been a nice proposal, or Koo and Saleur put forward a nice proposal of how to approximate the Virasoro generators, or the generators of conformal symmetries for a critical quantum lattice system, or in terms of data from a critical quantum lattice system. And how do they come up with their formula? Well, it's essentially by analogy in the following sense. So they say, okay, if you start from the Hamiltonian density of an assumed CFT model in the continuum, then this is essentially given by, I mean, this is all formal, but the idea is that it's essentially a linear combination of the chiral and the anti-chiral stress energy tensor. And now this the Fourier transform of this Hamiltonian density then is related to the Virasoro generators of the chiral and the anti-chiral part. And you can actually recover these Virasoro generators by just considering a certain linear combination of the Fourier transform of the Hamiltonian density and its commutator with the Hamiltonian. And so what the proposal they put forward is essentially to interpret this formula here as the definition of the Virasoro generator at a finite length scale as well. So they basically replace all the quantities that appear here by corresponding lattice quantities and declare this as an approximation to the Virasoro generators. And what we did now is that we show in a certain sense that these operators really converge in the scaling limit, so formally in the limit n tending to infinity to the actual Virasoro generators now, the model. And in a sense, in this fermionic model, we are in a very convenient situation because we already know that this has a, we have shown that it has a continuum limit, and we know that this continuum limit actually admits the representation of the Virasoro algebra. So we basically know what kind of limit objects we want to approximate. And yeah, as I said, the convergence is of course expected in the two chiral subtheories of the model. So what we do is now, as I said before, we split our one particle space into its two chiral components and restrict our state to these two chiral subtheories and carry out the scaling limit procedure I was describing before with respect to these subsectors. And then we find that also via this restriction procedure, we obtain the correct scaling limit. And in the massless case, we actually recover the one particle projections of the corresponding chiral subsectors are given by the so-called Hardy projection, which is exactly the thing you would expect to find. Now, we can also compute what these Koo-Saleur approximants for the conformal generators are in this setting. And yeah, because of the kind of quasi-free nature of the problem, they are actually just given as certain second quantized operators of, again, some one particle operators. And what we now have to show is basically that these objects converge to their continuum counterparts, which we also know to be second quantized versions of certain one particle operators in this case. For example, you can find this in the book by Evans and Kawabayashi on operators, algebras, and quantum symmetries. And now the question is, in which sense should these operators actually converge to their continuum counterpart? And the appropriate sense is quite similar to the one I was describing for like the dynamics. So what we are doing is we look at the Koo-Saleur approximants, which are actually objects in the fermion algebra at an effective scale. And then via our inductive limit construction, we can promote them to the inductive limit algebra. Then we have our representation of the scaling limit, which we constructed from this renormalization group procedure, and then they act on the continuum Hilbert space of this free fermion model in the continuum. And there we can compare their action to the action of the actual Virasoro generators. And what we show then is that in an appropriate sense, these operators acting on this continuum Hilbert space, they converge to these Virasoro generators. And in this sense, here you have a recovery of conformal symmetry. And yeah, to state like the main result here, so if you use this wavelet implementation of the renormalization group, then the statement is that these Koo-Saleur operators, if you represent them in the continuum limit Hilbert space, then they converge strongly to the Virasoro generators on a certain dense common core for the Virasoro generators. And this dense common core is itself encoded essentially by the image of the one particle vectors at fixed scales into the continuum using the asymptotic one particle method. And then, and then you use this one particle subspace to generate certain finite particle number states in terms of these vectors. And on that dense subspace, you have a strong convergence of these operators. And similarly, instead of using this wavelet approximation, we can also do a kind of momentum cut of implementation of the renormalization group. And then we can also show that we not only have the convergence with respect to the usual Fock representation of the CAR algebra, but we can even go to the scaling limit representation, which in the case of the Schwarz-Nerveux sector or the Ramond sector is actually a representation which has non-vanishing central charge for the Virasoro generators, and there we also have this strong convergence. Yeah, but we need a slight modification of this renormalization group transformation because the convergence here is in a certain sense stronger than the convergence we were looking at here, and at least to the point we're understanding it at the moment, using a momentum cutoff implementation works slightly better for the convergence here than this wavelet interpretation. But we can still combine this, and that's like this next remark here. So here I was just looking at the Virasoro generators themselves, but if we want to look at certain localized quantities, we can also consider their lattice smeared out versions. So for certain lattice smearing operators, and provided these lattice smearings again converge in a similar way as I was describing for these one particle vectors in a certain Sobolev type norm, and we can show that these smeared out operators, where we define the convergence of these smearing functions in terms of these wavelet RG, then we will also have convergence of these operators in this stronger sense, where we have the non-vanishing central charge. Then usual results like the Trotter-Carter theorem actually show that we can also convergence of the associated unitary groups, which then implement finite conformal transformations in the scaling limit. And now another interesting result, and that brings me basically to the setting of quantum simulation, is that from this convergence result for the generators, we also obtain convergence results for the correlation functions in the following sense. So if we take certain convergence sequences of operators of our lattice models, which are where convergent means this kind of limit here should exist. So if you compare an operator to its image under these fine-grained maps, if you start from a coarser lattice and you demand that this goes in norm to 0, that's called a convergent operator, then the corresponding correlation functions, where you can use some dynamics which are either given by the effective Hamiltonian or, for example, the certain self-adjoint linear combinations of the Virasoro approximants, then these correlation functions converge to their continuum counterparts. So in this sense, you get an approximation theorem for the construction of the correlation functions, dynamical correlation functions of your continuum model. And so this is the statement where basically these A and B are fermion observables, but this can again be extended also to correlation functions for example, the algebras generated by local conformal transformations, so basically so-called Virasoro correlation functions. And yeah, this in a sense provides a useful statement for the simulation of fermionic CFTs on quantum computers, because here we not only get this convergence result, but we can actually quantify how good or how fast this convergence happens in terms of n, which then gives you direct error bounds, because this n is directly related to the size of your quantum simulation. And yeah, as another remark, so you can also extend this argument to encompass so-called non-abelian currents. So you can get certain WZW models from the same construction by basically using a certain free fermion representation of this current models. Okay, and I think I'm slightly over time, so let me just mention that also the construction of the disorder parameter works in a similar way. So this problematic object I was talking about before, so the string operator, which is necessary to get the actual order parameter in the end, that can be considered in a similar way. So you can either look at it as inducing a transformation of the fermion algebra or as a composite operator in terms of fermions. And what we have shown so far is that if you look at the induced transformation of this disorder parameter on the fermion algebra, then you can show its convergence using this wavelet implementation of the renormalization group transformation. But what we are still working on, and that's kind of a harder problem, is to show that the actual implementer itself converges in the scaling limit construction. So yeah, so in a sense, we have a candidate for what the disorder parameter should be in the continuum limit, because that's like known from work from the 80s and late 70s, but what we do not have achieved so far is the showing the convergence of this thing as a quantum field in the end, because it's known that this object is a kind of local quantum field, and what we only could show so far is that the induced transformation of this quantum field on the observable algebras, that this thing actually converges. Okay, and maybe I should stop here. So there's a kind of natural extension to anionic chains, which uses the braiding operation, but yeah, I think this would take maybe too long to discuss this as well. So let me just finish with some future directions. So of course, I mentioned this construction of these WZW models, and so far we only considered this for central charges which are essentially larger than one, because we use a kind of tensor product construction of prefermions, but using the so-called Sugawara construction and the coset construction, we should. My impression is that it should also be possible to use the same thing to get the models for central charges smaller than one. As I said, there's a natural generalization to anionic chains. And of course, it would be very interesting to compare this approach to other methods, for example, using vertex operator algebras and wavelets, and also to clarify how these methods could be related, if possible, to these Schramm-Löwner evolution methods for the scaling limit of the Ising model. And then together with Stefan, also looking at the recovery of fusion rules from the lattice directly and its relation to defects. And yeah, and another interesting question, of course, would be to go to higher dimensions in this setting, because the setup itself is not really restricted to like these 1+1 dimensional models. But of course, if you go to higher dimensions, then you expect that dealing with the convergence of these ground states is actually something which is then plagued by additional renormalization group or renormalization conditions which are not appearing in these 1+1 dimensional models. Yeah, there we basically get away with normal ordering, but of course that's not sufficient in higher dimensions. And then related to the quantum simulation, it would be actually interesting whether we can get refined error bounds, because some of these error bounds are just implicitly given because they use the Trotter-Kato theorem where to get the approximation of unitaries, and there the error bounds are not very explicit, and I'm not aware of any method to get explicit general error bounds. So I think a similar issue is faced by people who do these things to approximate, for example, partial differential equations in the continuum, where certain lattice approximations there you face a similar issue, and it's basically done on a case-by-case method. But yeah, I would be happy to hear about any more general things there. Okay, thanks.
Thank you. Any questions to Alex? Raise your hand or speak up. Okay, maybe I can break the ice. I wasn't. I mean, clearly this free fermion representation helps, and yet you were talking about minimal models, I suppose, in the end. Let's see, less than one.
Yes.
So I didn't quite get what you precisely had in mind to get the other minimal models. Could you elaborate on this?
Yeah. So one possibility there is to from our free fermion construction, we can basically by using multi-component fermion versions of this construction, we can implement we can get the convergence of Wessel-Witten currents which have a central charge, which are in representation with central charge which is larger than 1. But then you can combine this with this coset construction where you have an embedding of one to the other, and then doing the coset construction you can get the central charge below 1. And to me it looks at the moment like that this construction is actually compatible with the scaling limit procedure we were using here.
Because there are also other lattice representations of minimal models. For example, in the very thick book by Di Francesco et al., you will find all sorts of SOS type models. So you're not having in mind using those as a kind of point. I mean,
yeah, no, in this specific case at the moment not, because the other one was a bit more natural because we have a kind of nice starting point to carry out the procedure. But yeah, in relation to that, I was also in this context of these more general anionic chains, I'm looking at certain types of parafermionic models which are related to these end state or quantum real-time quantum versions of these end-state POTS models, where you would also expect to recover certain CFTs which have central charge less than 1 and which are not just free fermion theories. So one example would be one typical example would be this 3 states quantum POTS model where you have a parafermionic theory in the background, so it still has some integrability. So the question that there is whether we can use this parafermionic algebra in that case as the basis for the construction and then derive like certain primary fields as composite operators in terms of these parafermions in the end.
I see.
So similar, like for the Ising model, we have this basic fields which are given in terms of the fermions. Then, of course, to construct the whole model, we also have to reconstruct the other primaries. And they are like composite objects in terms of the fermions. And yeah, so far, we only have their convergence as automorphisms, if you want, of the fermion algebra, which is a bit weaker than what you would actually like to have. Because it would be nice to see the convergence directly at the level of the implementers.
Okay.
And, yeah.
Thank you. Other questions? Okay, that doesn't seem to be the case. Then thank you, Alex, for this talk on spin chains. Thanks. And I'll see you all back. Or see you all in Jochen. Could you help me out here? When is the next talk on Bahum?
We don't have a speaker yet, but it's probably in May.
Oh dear. Okay, it's in May with an as yet unknown speaker. See you all. Bye-bye.
Bye. Bye.